Centroids and centers of gravity for distributed forces. Distributed forces, what this is talking about is instead of something that is concentrated at one spot, you have a pile of sand or some three-dimensional object where the forces are happening all throughout the entire object. And what we want to do is take this distributed force and turn it into a single force that acts at a single position. And the spot where the force is going to act is the centroid of the object, or the center of gravity if we're talking about the object with respect to something happening on Earth, which is usually the case for us. Now, Wikipedia has a great little list of centroids, a table with common shapes, and it shows you for all of these different shapes the X and the Y position, where kind of, even though weight is acting throughout the entire object, it kind of feels like weight is acting at this one little spot, and they'll tell you for some homogeneous object where it would tend to act at for that. Here's a couple of other pictures to throw up. So you have an object and there's weight acting through the entire thing. Like every single atom on this has weight, but all of those individual little weights add together such that the weight is going to act at a single spot, and it's the spot it balances around. So if you add up all the weight for, like, say, this tightrope walker, even though there's weight over here and over here, if you drew a free body diagram of it, what we could do is we could add all these individual pieces together, and it's kind of like the whole thing is just balancing on his toe or on the bird's beak for this thing. And it comes back, finding the position of it, it's an equivalent force problem. So back from chapter 3, if you remember this homework problem, where you have a bunch of forces and a bunch of moments, and we want to simplify this. So we don't want to have to worry about what every individual atom is doing. We want to add it all together and come up with just a single force and the position that that single force is acting. So let's review how to create an equivalent system, because that's what you're doing to find the center of mass of something. So here we have a beam, and the beam has a bunch of forces acting on it. So now for the distributed load, that would be like a pile of sand, okay? And every grain of sand has a force acting on it, but we don't want some big, huge, complicated system, right? We want to just add all this stuff together and find one force, and not just one force, we want to find where that force is acting so that it has the same rotational tendencies, the same reaction at the supports over here. So everything is going to be equivalent, and we're just trying to simplify the system is all we're trying to do. If you remember how we did this in chapter 3, there was kind of two steps. So that the first step was finding an equivalent force and moment pair, and then the third step was to place that force at just the right distance that it would also create the same rotational tendencies as well. Now, so let's just do this example real quick, and then the distance where we're putting this force, that is the centroid of the system. Okay, so what force are we talking about here? Well, you just add up all the pieces. So in this case, 200 plus 300, the overall force is going to be 500 newtons. So if you had a pile of sand, if you added up each little grain of it, just F1 plus F2 plus F3 plus all of it together, that would be the magnitude of the total force that's acting on it. So 300 plus 2 and 500, the total force. The next spot is we have to figure out what position the force is acting on, and that is a moment calculation. So you can take the moment around any point you want and get the same result, but just because we think in left to right over here, let's take the moment around point A. Okay, so if we took the moment around point A of our original system, and we're going to have to take every force that's acting on it, R cross F, R cross F. So for the grain of sand, it would be from A to the first grain of sand, from A to the second, all of these R cross Fs, and we want this to be equivalent to D cross F. Okay, so from A the 300 Newton force, that lever arm is 0. So the 300 Newton does not cause rotation about A, so we can get rid of him. Over here, the 200 Newton, that does have a lever arm. So we say 3 meters times 200 Newtons. There's a rotation that's created over here from that. So 3 times 200, and then we also had this external moment applied, 400. So for this one, the equivalent system would be a force, 500 newtons. And if we applied that force at A, we would also have to add in this 3 times 200, so 600 plus 400, we get 1,000 Newton meter moment. So we would say that an equivalent system to all of this stuff would be a single force and a moment of 1,000 newtons. But now we want to get rid of that moment too. So 1,000 Newton meters, how can we move this force over to just the right spot so that we have the simplest combination, just a single force at the right spot? And again, this distance, that's the centroid. This is going to be the centroid of the system. Okay, so we have our 500 Newton force, and 500 times 2 is 1,000. So if we just put this force 2 meters away, this combination at that spot gives us the same results as over here. So if we were to find the reaction at the supports and just look at how the whole system behaved, we can model it with everything piled at this one little spot, and we know where that spot is, and that's the point of centroids and centers of gravity. It's just an equivalent system. So we're taking all the forces, we're adding the forces together into just one force, and we're finding the position in that pile of sand that it feels like the force is acting. And in reality, in real life, it does feel like all of these little grains of sand are adding together to just one force at one position. So it really does behave like everything is piled up on that one spot. Let's go through an example of just a randomly shaped object here. Okay, so this object is made up of a bunch of atoms, and each atom has a weight and is pulling down with some force, but we don't want some big complicated system. So we're going to try and add all of these little individual forces together into just one force, and then we also have to find the point that that equivalent force is acting on. So it feels like everything is added together to just one force at one point. This would be a concentrated load. So we're going from a distributed load to a single concentrated load, and it's just a way to simplify our system. So where is this point? How can we find it? Let's go ahead and take our object and break it up into some pieces. Okay, so a rectangle. We know where the center of a rectangle is. A triangle, we can look this up in Wikipedia and find where the center of that guy is. So if we can break our object apart into some normal, commonly found shapes, this is the easiest way to start through this. And remember, we're going to find the equivalent system through a moment calculation. Let's pick a point, and you can pick whatever point to take the moment around you want. It doesn't end up mattering, but let's define our coordinate system. So our object is kind of sitting over here with the corner on the origin, and we're going to take the rotational tendencies around the origin. And we could have taken the rotational tendencies around this point, but let's just, again, think from left to right. So R cross F. Our green object here has some weight from this, and if we look at the rotational tendencies from this chunk of it, we have the center to the rectangle, right? And then we can look at the triangle. The triangle happens to be a third the way from the base. So there's the position vector to the center of this triangle. And our last rectangle, again, we're just looking at where the center of the thing is. So if we add up the entire weight of this huge rectangle and look at the position that's acting on. So it's adding together all of these moments. So R cross F, R cross F, R cross F, just the position to each of these little pairs. Okay, and what we want is not some complicated thing. We want just one force, and where is that force acting? So the moment, the distance to the force over here at our simplified system is going to be equal to all of these little individual pieces added together. Okay, so here's the big equation. We have, right, the green square, x1, f1. We have the blue triangle. We have the big pink square, x. So we add together each of these moments, and we're finding just one force. So the force that's applied over here, that's everything added together, m1 plus m2 plus m3 times gravity. So each little piece added together, and then the overall distance to that force, this is the coordinate for our centroid. If you see a little bar over the top of it, that's the nomenclature that will be used to denote that that is the position to the center of mass of this thing. Rearranging this equation, we're going to take all of those forces added together, put it in the denominator, and then we have each of these little individual pieces on the top. So these are adding all of those moments together at the top. That's how you find the centroid. It's a moment calculation, and it's just looking at equivalent systems. So study that a little bit. Now this is the x coordinate of it. You can do a similar analysis to find the y position of it too. Okay, so not only does it have an x position, there's some sort of a height where it would feel like that force is adding together. And if you reorient this with respect to gravity, you could find that y position. Here's an example problem. We're going to find the centroid of this area shown. The first step in this is, how are we going to break this area up? So we can break it up a couple different ways. The easiest way to break this thing up is probably going to be into just two different rectangles here. So how would you define it? So if we say this is one big rectangle over here, and we can find the area of this rectangle and the center of where things are acting over here, and then we have this second rectangle. You can make this another color. If you have some markers or something to color on things and just keep track of what is what on here, that's kind of a good thing to do. So here's the second rectangle. Okay, so if we turn each of these rectangles into individual forces, so these two concentrated loads, and then we're going to add these two together, so that the final goal of this, right, is instead of, you know, a bunch of different atoms and they're all pulling down, we want just one force acting on it, and the location of that force and the magnitude of the flow. So looking at this, if you're going to balance this object on your finger, what point would you balance it around? So it looks like it's kind of taller, so we're going to be kind of above here, and so the final goal is we want to find just one force, and we want to see where that force is located over here on our xy coordinate. So we're going to just place our xy coordinate system so that the origin is over here at the corner, and we want to know the location of the centroid, so the xy pair that's going to balance this object. Okay, so let's scroll down here. I've got some tables made for you. So we've split our object into two parts, 1, 2, and we want to add up. And remember, it's a moment calculation, okay? So to get our centroid, our overall centroid times, and the area ratio is the same as the force ratio. So rather than looking at densities and thicknesses and calculating the whole weight, we're going to base our moments now entirely just off the areas instead of forces, but they're proportional to one another. Okay, so it doesn't really matter. So we need all of these R cross A pairs. So instead of R cross F, it's R cross A, and we're going to add together what's happening with our first little rectangle, our first little chunk, and then our second little rectangle. So what's the area of shape number 1 here? Let me just zoom in on here. First, let's get the areas, because we need this overall area of everything. So if we call this our first rectangle, we have 5 plus 1 plus 2, and then it's 1 inch thick, so we have equals 1 inch thick times 8 inches tall, 8 inches squared for our tall rectangle. And then this little guy over here, let's see, 4 minus 1. So he is 3. Do you see where I'm getting these dimensions? Let me draw these in here. Okay, so this distance here is going to be 3 inches. And then this distance here is 1 inch. And so the area for this guy over here is going to be equal to just 3 times 1. So not too bad. So and these are in inches squared. Okay, what's the next thing we need to do? So the next thing we need to do is to find where the centroids of each of these rectangle is. Okay, so where's the centroid of the number 2 rectangle and the centroid of number 1? With respect to, see how we have our coordinate system on here? So 0, 0 is down here at the lower left-hand corner. Okay, rectangle number 1. And remember, you can put these YouTube videos on fast forward mode if you want to watch it faster. Here we go. So we're going to concentrate on this first rectangle over here. And we're measuring everything with respect to this XY coordinate system. Okay, so we want to find the XY position of the center of this rectangle. Now it's just a rectangle, so the center of it is in the middle of it. Okay, 1 inch, so we're going to be going over ½ an inch. So here's the center in the X direction, 0.5 inches. And for the Y distance, okay, so we're going to go up halfway. So remember, the overall height of this is 5 plus 1 plus 2. This is 8. And so the overall height to the center of this rectangle is 4. So we're just finding the XY positions of the center of this rectangle. Then we can do that for our other chunk too. Okay, so let's call this our green rectangle over here, and we want to find the center of the green rectangle. So where would that be? So we know that this guy, let's see, it's 4 minus 1. So we have a distance of 3 over here. So from the edge, it's going to be 1.5, but we're not going from the edge. We're measuring this from our origin, right? So if we're seeing how far over from the origin we're going, that's going to be 1 plus 1.5. So our x distance in this case is going to be equal to 1 plus 1.5. So it's going to be equal to 2.5 over to the center of this green rectangle. And then to figure out how far up we're going to go, so how far up are we going to go? And let me erase this stuff off. So we have to walk up the leg of this thing. Okay, so all the way up 2 inches, and then we're going to walk up halfway through this rectangle. So we're going halfway through this 1 inch to the center point over here. So for the y distance, it's going to be equal to 2 plus halfway through. And that's just the coordinates with respect to this origin. And that's what we're going to be taking the moment with respect to. Okay, so if we're going to rotate this around the y-axis, and we're doing kind of an R cross F sort of a deal. So we have some weight that's acting on this, okay? So we have a big force that's created from this chunk, and we want to see how much of a moment that force is creating around the y-axis. It's the distance to the center. So that's the next little thing we're going to be doing, is an R cross F and R cross F, and add together all of those moments. Okay, so let me zoom out again, and I'll get rid of this then, and hopefully that's not too confusing over here. So this is a part of the table where we're calculating those moments. And remember, the area ratio is the same as the force ratio. So instead of R cross F, it's R cross A, but we're just going to say, take those distances and multiply it by the area. This is all of those little chunks of the moment that we're adding together now. So again, here's the equation. We're getting all these little x times a or y times a. So we're just multiplying all of these moments out. So there's our y times a. The next piece is we're going to sum it up. This little epsilon, that's a summation sign. So we're just going to say all of the x times a's we're going to add together. If you grab the lower right-hand corner of that cell and drag it over, it'll copy that equation over. So that's all of the little y times a's. We're going to add those together. And we also, over here, we have to add all of our areas together too, right? So we have first rectangle plus second rectangle. So that's like the total force or the total area of the whole thing. So if we want our centroid, it's going to be all of the little bits added together divided by the total area. So the x is going to be all of the little bits added together divided by the total area. Okay, so that would be our x centroid. So let me just double click on that so you can see. So just all the bits divided by area, and then the y centroid is all the little bits divided by the area. So same idea. And once you get those x, y coordinates, come back to your system and plug it in. So where is that point on here? So if I plot 1, 3.6, so 1, just a little bit over 1, and then 1, 2, 3 and a half, 3.6 is going to be somewhere in here, right? So remember, it's 8 tall, and it's a little bit bottom heavy. So it's not going to be at 4. It's not going to be halfway through that 8. It's going to be a little bit more towards that chunk. So does that seem like a good spot for where the center should be? That seems pretty decent, right? That we're going to say that this strange shape, it's going to act like all the weight is acting at this red spot, and that would be where all of that weight is acting together. And then if you want to know what the force is, that's going to, if you multiply the area times the density and the thickness, that would turn into the force that's acting there. So if you want to balance this shape, it's going to balance around this point. It's going to move around this point. You'll also do these kind of calculations in dynamics as well, because the object tends to want to rotate and move, and everything's going to be kind of circulating around this center of mass, this center spot. So hopefully that wasn't too confusing.